Let's take a look at the graph 1 equals x squared, just from 1 to infinity. Okay, so this keeps going, some value of 1 here, and we want to know what's the area under this curve. Okay, and I think the big question here is, if it goes to infinity, is the area finite or is it infinite? And I guess another way you could look at it, is it necessarily infinite? If you go from 1 to infinity under 1 equals x squared, does that area have to be infinite because it keeps going forever? And it's an interesting question because it keeps getting smaller and smaller and smaller, right? So how can we figure this out? We can set up an integral. So let's look at the integral from 1 to infinity, right? This is what we want, of the function 1 over x squared. Now, this infinity is interesting because we have only dealt with integrals where the bounds are positive. And so it is a new concept to deal with integrals that have infinite bounds. And the way that you do this is the following. You consider it as a limit as t approaches infinity or any other variable, and you make a trade and you put the t in. Because now the integral is something that we know how to solve. We can substitute in for t in 1, and then we can wait and put in the limit at the end. Okay, this works. So we'll keep the limit as t approaches infinity here on the outside. Limit as t approaches infinity. And then we're going to go ahead and integrate. So when we integrate, we simply get what? Okay, well, it's x to the negative second. So in effect, we add 1. We get x to the negative first divided by negative 1. So we get negative 1 over x. And this is going to be evaluated from x equals 1 to x equals t, right? 1 to t. Okay, so let's do that. First we would put in the t, and we get negative 1 over t. Okay, I'll keep this limit here on the outside. Limit as t approaches infinity of, we got this negative 1 over t, and then we subtract, and that's plus 1 over 1, which is just 1. Now, the limit as t approaches infinity, if we look at this, well, clearly this first term goes to 0, right? We've done limits. And additionally, the second term, it has no t in it, it goes to 1. So it is a fact that the area under this curve is actually equal to 1. It is not infinite. And if you're, I don't know, you don't believe it, you can sort of like put in different values of t. You could start to add, more and more, like 1 to 2, 1 to 3, 1 to 4, 1 to 5, 1 to 10, 1 to 100, 1 to 1,000, 1 to 1,000,000. I mean, you can see that you're subtracting, you keep subtracting like smaller and smaller amounts from 1. You're getting closer and closer to 1. What in fact is the correct answer. Now, let's compare that with the following. Let's compare it with something very similar, and we're going to look at now 1 over x. Now it's hard for me to like precisely draw the difference between 1 over x and 1 over x squared, so my apologies. I mean, they kind of do a similar thing. Okay, not the best attempt, but what are you going to do? So we want the same idea, 1, and we want to know, okay, so what is this limit as, as x, as t, right, as the curve goes to infinity, right? We have an infinite area under the curve. Do we also get something finite here? Okay. Should be clear that if we have like a horizontal, right? Like y equals 1, I mean, if you have a horizontal and you always keep adding the same amount, you are going to get infinity. So let's see what happens here. Clearly it's not always going to be finite, that's my point. If it goes up, of course it's infinite. Okay, so what we're going to do, we're going to set up the integral again, and let's This time we'll do it, it's still going to be from 1 to infinity. In effect, the only thing that changes is that it's 1 over x instead of 1 over x squared. Okay, and so now we've learned the technique for doing this. We say, okay, this is the same as the limit as t approaches infinity, integral going from t to 1 over x dx. And now we go ahead and integrate. We know that that is the natural log of x, evaluated from t to 1. We still have this limit as t approaches infinity. Okay, and what we need to do now is we need to evaluate this at these different points. Okay, so we've got the limit as t approaches infinity. Just plug in now. Natural log of t. And we're going to subtract off the natural log of 1. The natural log of 1, e to what power is 1? It's e to the 0. Okay. So it's 0. I'll just write in the 1 for now. Okay, so that's 0. That contributes nothing. But what about this? Well, natural log is an increasing function. So as t gets bigger and bigger, it gets bigger and bigger. This is infinite. Okay? So this integral is actually infinite. And what we would say is that basically it's not a number, it diverges to infinity. Okay, that is the general idea here. We have a divergent integral. Now, okay, I tried to make this a little suggestive, but trying to make it a tad bigger. So what's fascinating is these are both decreasing functions. They're consistently getting smaller and smaller, but the area of one of them converges to infinity. Converges to 1. The area of the other diverges to infinity. So that is pretty fascinating in itself. These are called improper integrals. And improper integrals, they usually have an infinity in there. This is how you deal with it. You just make a change of variable, call it t, and take the limit as t approaches, whether it's positive infinity or negative infinity. Now, you can have some other types. And so let me show you another interesting type you could have. Let's consider the following. Consider the integral of, how about, let's look at 1 over the square root of x minus 3 dx, evaluated from 3 to 7. Okay, so why is this included here? Because 3 is not in the domain, right? When you plug in 3, you get basically infinity. So you do need to do the limit as t approaches 3. And let's go ahead and integrate this one. So it's just everything to the 1/2 power, right? And if you do everything to the 1/2 power, you add 2 halves, you get, it's actually negative 1/2, right? So when you add 2 halves, you get a positive 1/2, right? It's that thing to the positive 1/2 divided by 1/2, which is the same as times 2. So it is 2x minus 3. Okay, that's the integral. But now, because up here, okay, the 3 was undefined, I'm perhaps jumping in a step, and I should say, let's come back to that, I'll write it underneath. So we already figured out what the integral is. But what we need to do is we need to say that this is the limit as t approaches, and we're going to go from 3 to the right, because go from 3 to 7. Okay, because like with 1 over x, you can have divergences at 3. And now there's no issue with the bounds, because now this is an integral that we can do. Okay, you can't do an integral if if a or b is undefined in the function. I mean, how would I put this? You can, but you're supposed to use the limits, and this is is the recommended technique for doing it. So we already figured out, okay, the limit here is just 2 over root x minus 3. Because if you do the derivative, it's 1/2, the 1/2's cancel, and it's all the negative 1/2 this in the denominator, evaluated at 7 and t. Okay? Limit as t approaches 3 from the right. Okay, so let's do one term at a time. So 7 minus 3 is 4, 2 times 2 is, well, square root of 4 is 2, 2 times 2 is 4. And so the first term is just 4, okay? And then it's 4, right, because you just plug it in. Now, what about the t? Okay, so the second term would be then the minus 2 root x, sorry, not x, x becomes t. T minus 3. And then you still want to look at this as the limit as t approaches 3 to the right. But now it's pretty straightforward because, well, this is just 4. And this second term, well, if it approaches 3 to the right, I mean, that's just like, you can plug in 3 here, right? So you can plug in, it doesn't matter right or left. It's just 0. Square root of 0 is 0, and minus 2 is 0. So it is just 4, okay? So that's like a similar example. And in conclusion, let's do one more. Okay, let's look at the following. Let us look at the integral from negative infinity to positive infinity of 1 over 1 plus x squared. Okay. Now we've got 2 infinities, so how do we do that? Do we do like a t and an s? The technical sort of recommended approach is to actually to split into 2 integrals. Okay, so you can pick like a simple point like 0, which is defined here because, denominator is always positive. And so we could say, well, this now equals, it's going from negative infinity to 0, dx over 1 plus x squared, plus integral from 0 to infinity, dx 1 plus x squared. And, we can now move forward and sort of do 2 separate integrals, just like we did these 2 separate ones here. Okay, so these are both tangent inverse of x, right? And so this is tangent inverse of x, evaluated from 1. Now if we do the substitution, it's at t, right? So we're sort of like skipping the step here. And this is the limit as t approaches negative infinity. And then same thing on the right side, but we're going to have limit as t approaches positive infinity. And that's, but it's the same as tangent inverse of x. Okay, so, wait, what are the limits as t approaches positive negative infinity of tangent inverse of x? Okay, I think we need a drawing for this one. And if we want to try to draw it, so if you know that the tangent of x, let's just do a couple. So the tangent of x would be what? Tangent of x is sort of like this. Between negative pi over 2 and pi over 2 goes, sorry, hard sometimes to get these markers just right. Okay, it does this shape, and so for the tangent inverse of x, and importantly, this is negative pi over 2 and pi over 2, you basically have these asymptotes rotated. And so it looks like this. And this would be, so negative pi over 2, pi over 2. And it does something similar, it goes like this. And so if we check this out, so right as, what's happening? As x gets closer and closer to pi over 2, right, it sort of gets larger and larger. That's what you're seeing here. And so what ends up happening then, if we look at the graph here, So first of all, the tangent inverse of 0 is 0. So these first terms are just 0. Okay, so first term is 0. Then we're going to do minus what? Well, as it goes to negative infinity, as t goes to negative infinity, it goes to negative pi over 2. So we're subtracting negative pi over 2. This is in fact pi over 2. And then the second one, I got to write down this one is going to t and 0 as such. And so this one is now t goes to infinity, right? It's getting bigger and bigger. It's getting closer and closer to pi over 2. And the 0 is still 0. So it's plus pi over 2. So this, in fact, is equal to pi. Which in itself is kind of like amazing. I don't know. Is it amazing? I think it's fascinating. What the heck does 1 over x squared actually look like? I mean, there's the beginning of it, and it's going to do something like this. Okay, not quite drawn. It should be more centered, but how cool that that area is actually equal to pi. So this is the general idea of improper integrals. Whenever you have discontinuities, whenever you have infinities, make a change of variable by putting, say, the limit as t approaches the infinity or the discontinuity, withhold the limit, put it outside of the integral, keep it there, integrate like regular, and then when it's all done, it's time to plug in values. You have t's in there, and that's when you get in there and you solve the actual limits. So, and look, calculus has a lot of cool things. It's got a lot of surprises, okay? And this is one of the big surprises. So, think about this for a moment. You're consecutively adding, infinitely adding, right? Pieces of area, right? As this goes out to infinity. You never stop adding, okay? You're adding. But you do not end up with an infinite area, okay? You end up with an area that is precisely equal to 1. And when you do 1 over x, it diverges to infinity, even though it's like pretty close. And these are kind of bounds in the sense that if x is to higher powers, you're going to get convergence. And if x is to lower powers, meaning of the denominator of like 1, you're going to get more divergence. There's even a comparison theorem that you can use to sort of verify that. And this in particular we'll see later as a very famous series. I guess they're all, well, this one in particular, it's not quite a bound, but it's close, okay?